So today I'd like to start the section on the celestial sphere, okay, which is basically a big diagram. The celestial sphere is basically just a big diagram that you need to know how to use, okay? And it's based around the fact that if we sit here on the Earth, looking out at the stars, then take, for example, the Plough. Well, the Plough is what we would call it's a constellation. Sorry, it's not, is it? It's an asterism. But asterisms, constellations are all what we call line of sight effects, okay? If you look at the two stars at the end of the Plough's blade, then the two stars aren't actually arranged in space like that. One is presumably much further away than the other, okay? So when you look out at the night sky, you're kind of assuming that the sky is flat. Does that make sense? It's a strange thing to say, but the depth of the sky, the third dimension of space, when you're just looking at the stars and saying that one's rising, that one's due south, that one's setting, whatever, you don't really need to bother with it, all right? So a map of, if that's the Earth there, then say one star's here, one's there, that one's very far away, that one's quite close. It's not very helpful. The sort of accurate 3D picture of the universe for many things in astronomy isn't very useful, okay? Things like timekeeping and navigation, all sorts of stuff like that, we use the stars. It's much easier to think of it just like a giant sphere, all right? Just like a giant glass sphere. And that is, unsurprisingly, called the celestial sphere. Now, in the middle of the celestial sphere is the Earth, with its equator around the middle, which you should have heard about in geography, and its North Pole and its South Pole, okay? That's the Earth. You can find your position on the Earth by your latitude and your longitude. We'll come to that in a minute. But what we assume is that around the Earth is a giant glass sphere, okay? And on that sphere are stuck the stars, okay? There are many famous images of things looking like that, all right? Medieval pictures of the sky which show just this sort of flat surface, okay? In reality, some stars are over there, some stars are there, some stars are there. That doesn't matter, all right? When you think about a constellation, the distance of the stars is irrelevant. So we're going to collapse that third dimension for this particular section, okay? Now, to make the celestial sphere easier to manage, we mark in its North Pole, which is unsurprisingly called the North Celestial Pole, all right? And down the bottom, directly above the Earth's South Pole, is the South Celestial Pole, okay? Then what we do is we push out the equator. If you can imagine the Earth's equator being pushed out onto the celestial sphere, you get, again, you can probably guess, the celestial equator. Okay, the celestial equator is, a bit wonky that one, is the Earth's equator just pushed out onto the celestial sphere. Okay, now this is a very useful system for finding the positions of stars. Okay, let's just take the Earth for the minute. Here's the Earth with its North Pole, its South Pole, like that. If you live in Skipton, in North Yorkshire in the UK, then you can say whereabouts on the Earth you live by giving two coordinates, okay? Our latitude here is 54 degrees north and our longitude is 2 degrees west, okay? I'm hoping you've seen this sort of thing before in geography, that you know about latitude and longitude, but latitude is very simple. It's simply angle up or below the equator. You can have angles north of the equator, angles south of the equator. Your biggest angle north of the equator is going to be 90 when you get to the North Pole, and obviously 90 degrees south when you get to the South Pole, okay? The equator has a latitude of 0 in the middle, and when we say we're in Skipton, then we say latitude 54 degrees north means we could be anywhere, actually. You with me? If I say I live at latitude 54 degrees north, well, that's just a big circle, isn't it? There's a whole range of points on the Earth around that circle which have a latitude of 54 degrees north, okay? So a bit like, I'm sure you've done this in your maths books, have you done X and Y? Yeah. Have you played battleships? Yeah. 1, 2, 3, 1, 2, 3, 2, 3 and 3, 1, all that business. Like any flat surface, you can position things on there with just two numbers, okay? You just need two numbers to position an object on there, okay? And the Earth's surface, although it's curved, doesn't actually make very much difference. You still need two numbers. You can't do it with one. If I say I live at latitude 54 degrees north, no good, because because I could live in a whole bunch of places. Longitude 2 degrees west, well, it's a bit tricky to draw in. There we have an important line on the Earth, which somebody basically picked. Its proper name, I believe now, is the prime meridian. Okay, meridian is any north-south line through the Earth's poles. All right, so there's a whole pack of meridians. You can have any meridian you like. You can have a meridian through Paris, you can have one through Lisbon, you can have one through Moscow, wherever you want. But the one through London, in fact the east part of London, through Greenwich, has for many years been called the Greenwich Meridian, and now called the Prime Meridian, is basically the starting point for longitude. Okay? The Earth has a natural starting point for latitude, which is its equator. All right? Round and round, the Earth's all the same. Can you imagine the Earth spinning? There's no natural point to start your longitude from. Your x-coordinate, if you're thinking in maths book terms, you've got a natural 0 to your y-coordinate, up and down, which is the middle of the Earth. But that way, the Earth's completely symmetrical, it's just spinning round, isn't it? So you have to basically pick a point, and we've chosen that line from the North Pole to the South Pole through Greenwich and some other places. Okay? And Skipton is 2 degrees west of there. All right? Because the UK is tipped forward in latitude-longitude terms, we are actually 2 degrees west of that. So if you say 54 degrees north, 2 degrees west, that's that point there. Okay? There is no other point on the Earth that has those coordinates, and just like the XY things you do in your maths book, that finds the position for you. Okay? Now what we're going to do is exactly the same thing on the celestial sphere. But obviously the points on the celestial sphere are not places on the Earth, they're objects in the sky. All right? So you might look at a particular star and say, right, it's just there. How can I say its position? Okay? And a good way to think about this is to basically say, well, we're going to do the same thing as latitude and longitude. The surface of the Earth is the surface of a sphere, so the surface of the celestial sphere is the surface of a sphere. We can basically do the same thing as latitude and longitude, and that's a really good way to think about the first part of this section. We're finding positions in the sky. Well, not really, because we're not bothered about depth. We're finding positions on the celestial sphere, and we do that with the celestial equivalent of latitude and the celestial equivalent of longitude. Okay? Let's do the easier one first. The equivalent of latitude in the sky, the equivalent of latitude on the celestial sphere is called declination. Okay? And if you're thinking it's like a sky version of latitude, you're not far off. Okay? That's a good way to think about it, but it has some important differences, as we'll see. First of all, you start at the celestial equator, which is 0, so you can think it works in a very similar way to latitude. And you can have declinations above the celestial equator, you can have declinations below the celestial equator. Okay? Now, if your declination is above the celestial equator, it is referred to as plus, not north. And if your declination is south of the celestial equator, it's referred to as minus, not south. Okay? This is a very common mistake. People quote declinations, but then they put north and south after them. All right? And that's not right. All right? So the thing to remember is north and south basically becomes plus and minus. All right? It's north and south on the Earth's surface. It's plus and minus on the surface of the celestial sphere. It has the Greek letter delta. Start again. The Greek letter delta, which looks a bit like that. Okay, like a swirly D. And you might say, I've got a declination, let's say, of plus 32 degrees. You can't say 32 degrees north. All right? So declination 32 means you are 32 degrees above the celestial equator. If it was minus 32, you'd be 32 degrees below the celestial equator. All right? So plus and minus does the job of north and south on the Earth. Okay? Biggest declination you can have is obviously plus 90 when you get to the North Celestial Pole. And the lowest declination obviously is minus 90 when you get to the South Celestial Pole. Okay? And as I said, if we're plotting positions on the sky, we're going to need two numbers. Just like on the Earth, to find your position on the Earth, you need two numbers, latitude and longitude. we need the same thing in the sky. All right? So the first number, declination, is simply angle above, angle below the celestial equator. Very, very similar to latitude, but the only difference is, of course, it goes plus or minus, not north and south. All right? Don't put declination 32 degrees north in the exam. You will lose a mark for that. Okay? Now, the celestial equivalent of longitude is a bit more tricky because, again, just like longitude on the Earth, there's no natural starting point. All right? Now, in the case of the Earth, lots of countries had a big fight over it using ships and cannons and things, and the UK won, so that's why it goes through Greenwich. Can't quite do the same thing in the sky. We have, however, got a natural starting point, and to do that we need to put in a line that you've met before, which is the path of the sun around the sky every year. Okay? The sun is not fixed on the celestial sphere. If it were, then what would our year be like if the sun didn't move around the celestial sphere? Yeah. You'd just have the same daylight every day, wouldn't you? Okay? But sometimes, as we know well recently, the sun is very low down in the celestial sphere. It does a very small path through the sky every day. It doesn't spend very long, it doesn't get very high, and we call that part of the year winter. In some parts of the year, the sun is very high on the celestial sphere. It spends a long time in the sky. It takes a very high arc through the sky, and we obviously call that summer. Okay? So as you know, the pattern of the seasons is defined by the motion of the sun around the celestial sphere. Okay? Don't forget the once a day, once every 24 hours diurnal motion, the fact the whole thing goes around once a day, we're kind of ignoring that. All right? But on one day, if the sun goes around the sky, on the next day, it will go around a slightly higher arc or a slightly lower arc, and every day it changes, and it takes it 365 1/4 days to go all the way around. Okay? This line is called the... That's it. This line is called the ecliptic. Again, the three words not to muddle up in astronomy: eclipse, ellipse, and ecliptic. They all mean completely different things. So this line is the ecliptic, a good definition, the apparent yearly path of the sun around the celestial sphere. Don't put the path of the sun across the sky. Path of the sun across the sky today is that. It's got nothing to do with that. The point about the ecliptic is tomorrow the sun will take a slightly different path because it's moved its position on the celestial sphere. Okay? The stars all have fixed coordinates pretty much, but the sun doesn't. You can look up the sun's coordinates throughout the year, and every day of the year it has a slightly different position. In fact, that is what we mean by the year, don't we? If the sun didn't move, there wouldn't be a year. You might be thinking secretly, actually, the sun doesn't move and the earth goes around it. But again, this is celestial sphere. I know this is completely wrong with everything going around the earth, but actually it makes no difference. If you want to predict when's that star going to rise, what latitude am I at, all those sorts of things, it's much easier to think of the earth as stationary. Okay? Now, there's the ecliptic, and the ecliptic famously crosses the equator. There are two very important points. I've drawn them a bit wonky, actually. There are two very important points on the celestial sphere where the ecliptic crosses the equator. Okay? The one where it crosses going north, what season will that be for us in the northern half of the Earth? Where the sun's crossing from the lower half to the upper half.
Spring.
It's spring, isn't it? All right? And obviously on the other side, it's going to be autumn, isn't it, where it drops from the top half to the bottom. Okay? Now, this point on the celestial sphere is called the first point of Aries. Okay? Because it's in the constellation of... Yeah, you'd think, wouldn't you? It's not anymore, it's wandered. I think it's in Pisces now. But in principle, yes, it's in the constellation of Aries, whatever. Okay? And round the back here, you have the first point of Libra. Okay? And that's the basic idea which we've come across before, which is the ecliptic goes through certain constellations. Just before Aries is the constellation of Pisces. Just before that is, I think, Capricorn, isn't it? Or whatever, and so on. And these are the constellations of the... That's it. So another word you need to know for the exam is the zodiac. The 12, although arguably 13 constellations which the ecliptic goes through, the sun obviously travels through those constellations every year, and that's why if you're born on a certain day in March, people say you're born under the sign of Pisces, because on that particular day the sun was in that particular constellation. Okay? Now this gives us a handy starting point for our second coordinate. A bit like the prime meridian, if you can imagine a line, it is a meridian obviously, through the first point of Aries. I'm not doing it very well. Got the first point of Aries too close to the middle of the diagram. Can you imagine a line through the first point of Aries? From the North Celestial Pole to the South Celestial Pole through the first point of Aries. Okay? That's our starting point for our longitude. For our equivalent of longitude, which has a very grand name, it's called right ascension, or sometimes just RA. Okay? So you have to have two coordinates. We've got declination and we've now got right ascension. Now right ascension is quite different to longitude. It doesn't have degrees east and west, which is what longitude has. It works in a slightly different way. As you move away from the first point of Aries, which is obviously 0 right ascension, you go to 1 hour, 2 hours, 3 hours, 4 hours, and so on. It ticks off in hours from the first point of Aries all the way around. The last mark before you come back to the first point of Aries is therefore 23. Okay? It's closely linked obviously to time, as we'll see a little bit later on, but right ascension is not measured in degrees. In one sense, actually, it's a bit easier than on the Earth, because if you said I've got coordinates 54 degrees, 2 degrees, you don't know, do you? Does that mean 54 latitude too long, or 2 longitude 54? You don't really know, do you? Whereas here, look at the coordinates. If you've got something like 3.5 hours, it's really obvious, isn't it, which one's the declination? It's the one with the degrees on. Which one's the right ascension? It's the one with the hours on. Okay? So declination is measured in degrees, a bit like latitude, but right ascension is measured in hours and minutes. Okay? And you might think, well, why is it measured in minutes and hours? It's because it's closely linked, obviously, to the rotation of the Earth and to time, as we'll see a little bit later on. Okay? But it means I can now give a coordinate. I can say this particular star, much like 32, does it? Like 62, I think. I can take that star there and say, right, well, it's 62 degrees above the equator, so it's got a declination of plus 62, and its right ascension, if I draw a line from the poles like that, it's about 3.5. A bit cheating. You with me? Where does the meridian from the north to south celestial pole that goes through that object, where does it cut the equator? Gives you its right ascension. Okay? So if I said to you declination 62, right ascension 3.5 hours, you'd find that point, and a bit like battleships, 3 along, 4 up. That's your point. Okay? Is that making sense? Happy with that? Right, let's try and use it then. Let's see if we have actually understood it. Let's use the Earth. So again, do think of it like latitude and longitude. It's very, very similar indeed. Okay? Let's perhaps take the sun. All right? The sun has some important dates. One of them is the 21st of March, which is when it's here. So on the 21st of March, the sun is there, at the first point of Aries, and that date is called the spring equinox. Because on that day, every point on the Earth gets 12 hours day and 12 hours night, hence equinox. Okay? On the 21st of June, it reaches up here, and that, of course, is called the summer solstice. Okay? On the 21st of September, roughly, it obviously reaches the first point of Libra around here, and that's called, unimaginatively, the autumnal equinox, or the autumn equinox. And then on the 21st of December, it reaches here, which is known as the winter solstice. Okay. What I'd like you to do, I haven't got very much room, unfortunately. Can you write down the declination and right ascension of the sun, can you work out what goes in those 8 boxes? Have a think, see what you can do. A minute or two. Can you work out what declination and what right ascension the sun would have if it was here, here, here and here? One very important thing I haven't told you, which I need to do, is that angle there is 23.5. I've done that before. The obliquity of the ecliptic, as it's known, the amount by which the ecliptic is tilted off the equator. All right, it's due to the Earth's axis being tilted away from the solar system, and that's 23.5 degrees. You'll need to know that to do the declination. Well, I'll do the first one for you because it's easy. Yeah? Thinking of your XY graph paper, which I've just rubbed out in your math book, first point of Aries is like the 0, 0, the origin, the 0, 0 point in the corner. Okay? So, declination of 0, when the sun is here, let's just call them A, B, C, D, shall we? It's getting a bit confusing. Point A, point B, point C, point D. At point A, the first point of Aries, the declination is 0 because it's on the equator. That's the definition of the first point of Aries, is where the ecliptic crosses the equator. So actually I know also, can I fill in that one? First point of Libra, at the autumn equinox, that's when the sun comes back down and crosses the equator again. On those 2 days, the declination must be 0. Okay? Right ascension, well, right ascension starts from the first point of Aries. The first point of Aries, as I said, is the equivalent of your 0, 0 in your math book. When you do an XY graph in maths, you have a 0, 0 point, and that's obviously that point there. Okay? 21st of June's a bit more interesting. How far round the sky are we? What fraction of the sky have we gone round? It's a quarter, isn't it? So if it's 24 hours of right ascension around the celestial sphere, the summer solstice, which is here, I think you can see is going to be 6 hours. And in fact, we can do the rest, because then the first point of Libra is going to be 12, and the winter solstice must be 18. The 2 equinoxes and the 2 solstices split the year up roughly into 4 quarters, doesn't it? All right. So you're not surprised to see 0 right ascension at the first point of Aries, 6 at the summer solstice, 12 at the first point of Libra, 18, there it is. You see, 18 when the sun is down here at the winter solstice. Okay. Declination on the 21st of June.
20 plus 24.
Yeah, because if you look at the angle there, it's plus 23.5. It never hurts to do a plus sign. I know 23.5 is plus, and you wouldn't need it because obviously that's understood. Just make sure, are you putting in your plus and your minus, and remembering not to put north and south. Don't be tempted to call that 23.5 degrees north. Okay? Now, down here, can I convince you it's the other way down? So this will be minus, all right? Not 23.5 degrees south. At the winter solstice, the sun has a declination of minus 23. That's significant because, of course, that's the lowest declination the sun ever reaches, and that one's obviously the highest declination it ever reaches. Okay? Now, here's the celestial sphere again. It's squashed today. Okay, North Celestial Pole, South Celestial Pole, Celestial Equator, there's the Earth. Okay. Now, what we've drawn there, I think in computer gaming terms, is what's called the God's Eye view, where you're standing outside the celestial sphere. How exactly would you do that? What radius does the celestial sphere have? It's infinite, isn't it? So it's a bit of a mad thing. This way that we draw the celestial sphere is great, but you can never actually look at things from that point of view. All right? What we need to do is to think what life's going to be like for a little person, although that person's actually very large, or they're on a very small planet. What things are going to be like from there. So there's us in Skipton, let's say, looking out at the sky. The very important thing to realise, of course, is that the Earth gets in the way. Are you with me? Can you see down here on the celestial sphere? No, you can't, because the Earth's in the way. All right? Now, the Earth doesn't get in the way as much as if you were that big, but for ordinary-sized people on ordinary-sized planets, the Earth gets in the way big time. and it creates this kind of plate, this disc, okay, like that, below which you can't see. What do we call that? That great big disc of... It's the horizon, isn't it? All right. So can I point out to you that the diagram you just drew is great, but only aliens or God or whatever can see that view from the outside. Our view of the celestial sphere is very much from the inside. Okay? And the first problem that creates is your horizon. You have a huge chunk of stuff here which you can't see. All right? So, if you go out at night in Skipton and you look up at the night sky, you can see things like the pole star. You can see constellations like the Plough and all sorts of bits and bobs like that. The South Celestial Pole, the Southern Cross, you just can't see those from Skipton. You never get to see those constellations, and part of the reason is because your horizon gets in the way. Okay? So, having understood the basic bits of the celestial sphere, what goes where, right ascension, declination, the second thing you need to understand is the effect that the Earth has, which is to provide a horizon. Okay? Which means there's a good half of the sphere that you never see. All right? However, the effect of the horizon is a bit more complicated because, of course, the Earth goes round. Now, you can do this bit in two ways. You can either imagine the Earth spinning round inside the sphere, or you can think of the sphere going round with the Earth staying still. I prefer the first one, but it's up to you. So a bit of 3D visualisation now, which with my board marker I can't really do. Let's keep the sphere still for the moment. Okay. This horizon isn't going to stay in the same place all the time. At the moment I can't see some of the stars down here, but can you see what's going to happen over 24 hours? It's a bit like a coin. You know, when a coin is spinning like that, it's basically going to do that, isn't it? What would this horizon look like 12 hours later? It'd be the other way, wouldn't it? It'd be exactly the same angle, but it would have rotated round to there. So can you imagine that? Yeah? This, the northern tip of your horizon, does a great big arc like that, and the southern tip of your horizon does the opposite. Okay? So yes, I understand the horizon blocks out some of the celestial sphere because we're inside it, but it does it in quite a complicated way in that it spins round. It's not always the case. For example, a good example is take a star there. Can this person see that star at the moment? But, yeah, as the horizon turns round, once the horizon's over here, that star's going to be nice and high in your sky, isn't it? Okay? Now, what this does quite neatly is it divides the celestial sphere up into 3 sectors. And it'll be different, these sectors are different sizes for different places on the Earth. Okay? Here we are at Skipton with a latitude of 54 degrees north. That's going to be important in a minute. Can I convince you that things, well, tell me about them. North Celestial Pole, the Plough, and all the stars in this bit of the sphere. What view do we get of those in Skipton? Do they ever go below our horizon? They don't, do they? So these are, now you've got to be very careful. If they ask you to define this in the exam and you put always visible, is the pole star always visible? Not during the day, obviously. Can I always point? It's always up there. It's always due north over there. I'm now pointing at the pole star. I can't see it, of course, because the sky's grey, but in principle the sky's blue and so forth. These ones are always above the horizon. Don't put always visible because you can't see them during the day. So stars near the top of the celestial sphere, ones with quite big declinations. What declination does the pole star have? It's almost 90, isn't it? It's 89 point something or other. But with a big declination like that, you're always above the horizon. Not always visible, you're always above the horizon from Skipton with its latitude of 54 degrees. Okay? Posh name for these is the word you need to know. Things in this region, stars mainly, are referred to as circumpolar. Okay? Slightly misleading term. It suggests they circle the pole, which they do. Excuse me, it suggests they circle the pole, which they do. Have you ever seen a star trail picture? But in fact, all stars do, don't they? Some circle the pole and go below the horizon. So again, circling the pole isn't a good way to think about it. The best definition is they are always above the horizon. Okay? Tell me about the stars down here, below the southern edge of your horizon. They're always below, aren't they? Stars down here, that horizon that we've drawn can do what it likes. It can spin round and round and round and round. If, like the sort of penny going round and round, this horizon does this sort of thing all the time, what view are you going to get of this part of the celestial sphere? The answer is nothing. That's why you've never seen the Southern Cross from Skipton, because the constellation has a declination which puts it right into this region here. Okay? So the three regions are the circumpolar stars, the invisible stars, the underground stars, the ones you never see. What will objects in this region do, in the middle? That's it. Objects in this region are ones which will rise and set. They are visible from this latitude, but not all the time. Annoyingly, sometimes, they rise during the day. Yeah? In the middle of summer, Orion's in this region. The belt of Orion is roughly on the equator. So there's Orion, and unfortunately sometimes, like in the summer, it rises about 11 in the morning. Which means it goes around the sky and you just don't see it. That's why Orion is called a winter constellation, because it rises and sets at similar times to the sun in the summer months and at different times to the sun in the winter months. So it's a constellation you can only see in the winter. Okay? And these are the three regions that your horizon splits the celestial sphere up into. Okay? So your horizon, this is the big idea, your horizon chops the celestial sphere into three sections. Final thing to finish this off is to work out this angle. If I said to you, I'm thinking of a star, it has a declination of 40 degrees. Which of the three regions do you think it's going to be in? With a declination of 40. What do you need to know? You need to know, let's just put that middle line in. You need to know the tilt of your horizon. Okay? You need to know by how much is your horizon tilted. Now, the tilt of your horizon always looks very similar to your latitude. If we lived at the North Pole or Iceland, or if we lived near the equator, this would be much more obvious, but unfortunately we live in what are called middle latitudes. Between 0 and 90, 54, 40, they're very, very close to each other. And particularly if you draw your diagram as badly as I've done, that's why you're chewing the end of your pencils going, I'm not sure. Is that 40? Is it? Could be either, couldn't it? Very important thing you need to learn. This angle of tilt is not equal to your latitude. It's equal to something called your colatitude. Your colatitude is very easy to work out. You simply take your latitude away from 90. And be careful. Taking away from 90 is easy to get wrong. 54 away from 90, you want to say 46, don't you? Because you naturally want to take it away from 100. Be careful, away from 90, 36. I haven't drawn it very well on purpose. This angle of tilt, gentlemen, is, for Skipton, 36 degrees. Because the latitude of Skipton is 54. I know the horizon looks like it's tilted by 54, but that's because I'm rubbish at drawing. Okay? And what that means is the highest declination you can see from Skipton is plus 36. So the highest declination that will rise and set is plus 36. Anything between plus 36 and 90 will be circumpolar. Down the bottom here, you've obviously got minus 36, and anything below that will be invisible. And basically everything between plus and minus 36 will be rising and setting. Does seem a bit strange because it does look like your latitude, doesn't it? But if you lived at the North Pole, what's your latitude? What's your horizon going to look like? If I drew this for someone at the North Pole, well, I'm going to draw on. Here's the North Pole. Here's the person at the North Pole. They've got a latitude of 90 degrees north. It's the biggest latitude you can have, isn't it, on the Earth? Inside the celestial sphere, what's the tilt of their horizon?
0.
So 90 degrees latitude, tilt of horizon, 0. It's very hard to see from Skipton. 54, 36, 40, they all look the same, particularly I draw them. Let's go to the equator. Let's go to the equator. Let's draw someone on the equator. What's their latitude? 0. When you've got 0 degrees latitude on the equator, put you inside the celestial sphere, what's your horizon look like? It's like that, isn't it? There's your horizon. What's the tilt of your horizon? 90. Got to learn this. Your latitude, the tilt of your horizon, which is essential to this, isn't it? If you get this right, you can predict anything. Yeah, that one's circumpolar, that one's rising and setting, that one's invisible, but you've got to get the tilt of the horizon right. The tilt of the horizon often looks like it, but it's not equal to the latitude, it's equal to your co-latitude. All right? You know the sine and cosine?
Yes.
Yeah? So you know the sine of 30 equals the cosine of 60, don't you? Get it? Cosine. Co always means taken away from 90. Okay? That term doesn't matter too much. You've got to remember what to do. Okay? Think about the extremes. If you're at the North Pole, you'd have no tilt. If you're at the equator, you'd have 90 degrees tilt. Why are most observatories sited near the equator? You can, can't you? Sometimes the sun gets in the way, but what stars are totally invisible from the equator? None. Which stars are circumpolar? None. Can you see what's happened at the equator? Your horizon has gone vertical, so you lose that one. You lose that one. Do you see? And the whole, it's like living inside a barrel. The equator, everything rises in the east and everything sets in the west. All right? There's no tilt to it because your horizon is completely vertical. Okay? But the effect of the horizon, not quite as simple as it seems. Yes, you only see half the horizon. Beg your pardon. You only see half the celestial sphere at any time. But in quite a complicated way. The horizon chops the sphere up into 3 sections. Circumpolars, the invisibles, and the risers and setters. And to do this, you've got to get this angle right. And this angle, although it often looks like it, is not your latitude, it's your co-latitude. All right?